In today's class, we are going to look at the quantification of protein concentrations in a sample using the Biuret test. So we'll start our introduction by looking at the purpose of the Biuret test. So one purpose is to quantify proteins in samples, and this happens to be a quantitative analysis. The second is to confirm the presence of proteins, and this happens to be a qualitative analysis. And the third is to confirm the presence of peptide bonds. So now let's look at the Biuret reagent. The Biuret reagent is made up of copper sulfate, sodium hydroxide, and sodium potassium tartrate. So these are the three main chemical composition of the Biuret reagent. And the reagent is pale blue when pure, but turns purple in the presence of proteins. Let's look at the importance of each of the chemicals in the Biuret reagent. So we'll start by looking at the copper sulfate. The copper sulfate provides the cupric ions that interact with the peptide bonds in proteins. And the sodium potassium tartrate chelates or stabilizes the cupric ions, preventing them from precipitating out of solution and ensuring they remain available to react with the proteins. And the last is the sodium hydroxide. And this chemical creates the necessary alkaline environment for the reaction to occur. And one important thing that we also have to notice that the alkaline pH is crucial for the cupric ions to interact effectively with the peptide bonds. Principles of Biuret test. So under alkaline conditions, cupric ions from copper sulfate react with peptide bonds in proteins to form a copper complex that results in the formation of a purple color and absorbs maximum light at 540 nanometer. So this is the principle behind the Biuret test. Now, so let us look at a chemistry or a chemical reaction illustration of the principle behind the Biuret test for protein. So as we can see over here, this is our cupric ions from our Biuret reagent, and this is also our peptide bond from our protein. So what happens is that the cupric ions from the Biuret reagent reacts with the peptides bonds of the protein to form a peptide copper complex, which is normally seen as a purple color of the Biuret solution. That means the Biuret reagent or solution turns from a pale blue to a purple color to indicate a positive result. And this is just the experimental method of showing how a positive result and a negative result for a Biuret test. So if you can see, this is our sample and this is our Biuret reagent. So in the presence of proteins, a purple color is formed to indicate a positive result, and the absence of protein gives this color to indicate a negative result. Now let us look at the chemical basis for the reaction, or in other words, the chemical processes that are involved in the Biuret reaction. So first is the alkaline environment. So what we have to note is that the sodium hydroxide in the Biuret reagent creates an alkaline environment which is necessary for the reaction to occur. The next, each interaction with peptide bonds. And this is the second step or stage in the Biuret reaction. So in this alkaline environment, which is being created by the sodium hydroxide, Cupric ions from the copper sulfate interact with the nitrogen atoms of the peptide bonds of the protein. And this leads to the formation of coordination complex. And in this step, this interaction leads to the formation of a purple color copper complex. And the nitrogen atoms from the peptide bonds coordinate with the copper ions, resulting in a color change from pale blue to purple. So what we have to note is that the reaction of the nitrogen atoms from the peptide bonds with the cupric ions creates the formation of this complex. And the last is the proportional color intensity. And over here, the intensity of the purple color is directly proportional to the number of peptide bonds present and thus to the concentration of proteins in the sample. So what it means is that the more of the peptide bonds present, the higher the intensity of the color. Now let's look at the reagents and materials used in the Biuret assay. So the first is Biuret reagent. We also have a protein standard, and normally we use the BSA, which is bovine serum albumin, for plotting a standard or a calibration curve, our test sample containing our protein for analysis, and a microplate reader or a spectrophotometer. So now let's look at the test procedure for the Biuret test. So first is that to 1 ml of our test or protein sample, we add 4 ml of our Biuret reagent. We mix well and allow to stand for 30 minutes at room temperature. After which we determine the absorbance at 540 nanometer against a blank. And to prepare a blank, we use distilled water in place of the test sample and subject it to the same treatment as the test sample. So what it means is that, so in place of the 1 ml test or protein sample, we use 1 ml distilled water and add 4 ml of Biuret reagent to it. So we mix and allow to stand for 30 minutes at room temperature and use it as a blank against our test sample. So this is the result of our Biuret test. So we can see that a blue color indicates the absence of proteins and hence gives a negative Biuret test, and the formation of a purple color indicates the presence of proteins, hence indicating a positive Biuret test. Estimating the amount of proteins in test samples using a calibration curve. So first of all, what you have to notice is that we have to prepare a calibration curve from the known concentrations: 0.0 milligrams per ml, 1.0 milligrams per ml, 2.0 milligrams per ml, 3.0 milligrams per ml, 4.0 milligrams per ml, and 5.0 milligrams per ml. So after preparing these concentrations from our stock BSA solution, we subject each of these concentrations to the Biuret test method. So after doing this, we plot the obtained absorbance values against the known concentration. So as we can see from this calibration curve, so this happens to be the absorbance values that were obtained for each of the concentration. And the calibration curve also indicates a graph of absorbance on the y-axis against the known concentration on the x-axis. So the next important thing to do is to determine the equation of the line and use it to determine the amount of protein present in the test sample. So as we can see from this calibration curve, this is our equation of the line, which is giving us y equals 1.0177 s minus 0.0423. So where y happens to be the absorbance values obtained and the 1.0177 happens to be the slope or the gradient of the calibration curve, and S happens to be the concentrations in milligrams per mole on the x-axis, and the minus 0.0423 happens to be the intercept. So I'll just give a practical example of how to determine the protein concentration of a test sample. So let's assume that in our test analysis, we had the absorbance for our test sample to be 2.5. Okay, so if you want to determine the protein concentration of our test sample, we only make as a subject from the equation of the line over here. So if we are to make as a subject, our S will be equal to Y, which is the absorbance obtained, which is 2.5, plus the intercept, which is 0.0423, all divided by the 1.0177. So the value that we will obtain happens to be the protein concentration of our test sample. So this is how to use a calibration curve to extrapolate and determine the concentration of a test sample. Let's look at some of the advantages and disadvantages of the Biuret test. So we'll start by looking at the advantages. One, it is quick and easy. What we also have to note is the Biuret test is a simple and a quick way to determine if a sample contains protein, and it is independent of amino acid composition. So the Biuret test is not dependent on the amount or composition of amino acids in the protein. And the third advantage is that it has a stable reagent. As we on the Biuret test uses a single stable reagent, and it has precision. So over here, what we have to note is that the Biuret test has good precision and reproducible absorptivity values. So these are some of the advantages of the Biuret test. So now let's look at the disadvantages or the limitations. One, it's less sensitive. So the Biuret test is less sensitive as compared to other assays. So it also has interference. And over here, we have to note that the Biuret test can be affected by other substances in the sample, such as lipid, nucleic acid, ammonium salts, and biopigment. So these are all some of the interference that limits the Biuret test. So protein solubility. So over here, the protein that we want to use must be soluble for detection. And also, the Biuret test is not absolute. And in this case, one important thing that we have to note is that the Biuret test is not absolute test, as the colors need to be standardized for known proteins. And finally, there is a color variation. And over here, the Biuret test produces different colors for different proteins. For example, gelatin produces a pink color. So as you can see over here, this is a biuret test indicating um, a positive test result, though the color is not purple. So if you don't know that gelatin gives this specific color, and you happen to like perform a test and you see this color, you might think it's a negative test result whilst it is a positive. So these are some of the disadvantages of the biuret test. Thank you.